All right, let's take a look at this FRQ from the AP Chemistry 2025 exam. So for this first problem, it's giving us a mass spec graph, and it's showing us the relative abundance of each of the three isotopes for magnesium. So they tell us that magnesium 24 has a percent abundance of 79%, and then it's asking us for the relative abundance in part I here for the 25 and 26 isotope. So then they tell us that they're approximately equal in terms of their abundance. And so we just find the difference where we know they make up 100% altogether. We know that the magnesium 24 makes up 79%. And then so we get a difference of 21%. We divide that by 2 because there are 2 more isotopes. And then so each one has about 10.5% each. So then in terms of creating the points on the graph here, this marker here is, we can assume 10.0%. So for each of these lines, we want to make sure that they hit that part. And then that's going to be our part I. And then double I is then asking describe the difference in atomic structure that accounts for the difference in mass between magnesium 25 and magnesium 26. So all magnesium elements, or I should say that, all magnesium atoms have 12 protons, right? They all have an atomic number of 12. So that magnesium 25, we find the difference, has then 13 neutrons, and then magnesium 26 is going to have 14 neutrons. So in terms of our difference in atomic structure, that accounts for the difference in the mass between these isotopes. Magnesium 26 has more neutrons compared to magnesium 25, therefore that contributes to the difference in mass between these two. For the next part of number 1, they give us this diagram here. So they tell us that we have 2 separate solutions, right? We have beaker 1 and then we have beaker 2. In beaker 1, we have 1.85 times 10 to the negative 3 molar of MgNO32, so magnesium nitrate. And then in the second beaker, they have 2.80 times 10 to the negative 4 molar sodium hydroxide, NaOH. For part B here, the particle diagram shown represents a magnesium ion in beaker 1. So that's right there. Sodium ion in beaker 2 has a weaker attraction to water than Mg plus 2. Explain this phenomenon using Coulomb's law. So then Coulomb's law is the force of attraction is equal to K times Q1 times Q2 divided by R squared. So if we just think about this mathematically, we have a greater charge overall for magnesium, but they both have the same number of energy levels because they're both in the same horizontal period on the periodic table. So the force of attraction for sodium is then equal to, let's say, +1 divided by some value. And then the force of attraction for magnesium is equal to +2 divided by some value. Let's assume that these are fairly close, assuming that there's no other factor contributing to the radius. The force of magnesium is going to be greater because it has a greater charge overall compared to the force for the sodium ion, which has a smaller charge. So in terms of their relative charge, the greater charge is going to experience the greater force of attraction. Therefore, the magnesium ion should have a greater interaction with water, which makes sense based on what they're telling us about what's happening with the sodium ion in beaker 2. Now, in terms of the relative radii, well, if you have the same number of electrons, because if we think about these are isoelectronic, where when sodium becomes an ion, it has 10 electrons. And then when magnesium becomes an ion, it has 10 electrons as well. So they have the same number of electrons. And then so we have to think, well, what's the difference between them? Well, this one has 11 protons, and then this one has 12 protons. So if we still think about Coulomb's law, if Q2 is the same for both of them, and then Q1 is going to be different, where we have a different number of protons, we are going to experience a different force of attraction. So if the force of attraction is greater, that means that they are going to have a smaller radius. Those electrons are going to get pulled in closer. So magnesium ion is going to have a smaller radius in compared to the sodium ion, and so it is going to experience a greater force of attraction because of the smaller radius. For our next part here, for part C, it's asking us to calculate the pH of the solution. Now, the thing that's contributing to pH here is going to be the sodium hydroxide. So, sodium hydroxide is a strong base, and so it ionizes 100%. So there's two steps that we're going to have to do. So pH is equal to 14 minus pOH. We can calculate the pOH of the hydroxide solution, and then so if we take the negative log of the 2.80 times 10 to the negative 4, we're able to get a pOH. This gives us 3.55. Plug this back in, so now we have 14 minus 3.55. That's going to give us 10.45, or we could approximate it to become about 10.5. So then that would be the pH of beaker 2. For part D here, it's telling us that we're going to combine the two solutions. So it's the same beaker 1 and beaker 2, but now we're going to combine them into beaker 3. And then so it's asking us to calculate the concentration of the magnesium ions after the two solutions have been combined. So we're going to use the dilution expression, where it's M1V1 equals M2V2, where we have the initial molarity of the magnesium nitrate solution. So then that's going to be the 1.85 times 10 to the negative 3 molar, multiplied by its original volume, 35.00 milliliters. That's then going to be equal to our new molarity. And then we have the final volume, which is going to be the sum of these volumes here. So then we have 85 milliliters. So then we rearrange, we solve for the final molarity there. We then get 7.6. How many sig figs is this? 3 sig figs is the least amount. So 7.62 times 10 to the negative 4. That's going to be the molarity of the magnesium ions in the solution. Because when magnesium nitrate dissolves, it's just a 1 mole ratio between the magnesium nitrate and then the magnesium ions. So we don't have to multiply by any coefficient here. It's just going to be a 1-to-1 ratio. So that's going to be your answer for part D. Part E, I, is then saying determine the, or write the K expression for the solubility constant. So we have the given reaction here, and then KSP is equal to the concentration of the products because the solid is omitted. So then KSP is equal to the concentration 2 plus multiplied by OH minus squared because it has a coefficient of 2. So then that's our part for I. For double I, it is then saying, well, if you know that the concentration of the OH minus before the reaction takes place is going to be 1.65 times 10 to the negative 4, what is going to be the Q value of this reaction? And so we're able to reuse our answer from part D, which we just found right above. We have that molarity. So the molarity of the magnesium is going to be 7.62 times 10 to the negative 4. So then QSP is equal to 7.62 times 10 to the negative 4, multiplied by now our concentration of the hydroxide, which is going to be 1.65 times 10 to the negative 4, and then we square that, and then that is going to give us our QSP value. And then so we get 1.26 times 10 to the negative 7. So that's our answer for double I. For triple I, it's saying, using the reaction quotient, predict whether the precipitate will or should form as the mixture in beaker 3 approaches equilibrium, and then justify your answer. So we really just have to compare the magnitude of our KSP, which is there, and then our QSP that we just calculated. So in terms of the relationship between KSP and QSP, QSP is going to be greater. So because of this relationship here, we are going to form the precipitate more. This reaction is now going to favor the reverse because we want to decrease the Q value so it gets closer to K. And then so it says, predict whether the precipitate will form. Yes, the precipitate will form because of this relationship where QSP is going to be greater than KSP. So part F here, it's saying, well, in a separate experiment, the student adds HNO3 to decrease the pH of a saturated solution containing the undissolved MgOH2. Does the amount of the undissolved magnesium hydroxide increase, decrease, or remain the same as the nitric acid is added? And so when we think about what nitric acid is, it is going to be a strong acid. And so the strong acid is going to react with anything that is a base in the solution. And so from the magnesium hydroxide, we actually get hydroxide ions out of that process. And then so when we have the nitric acid reacting with the hydroxide ions that are in the solution, it is going to decrease that concentration, and it's going to form water and then the conjugate base, which is then just going to be the nitrate ion. And then so as a result, if we think back at this expression here, if we are now having a decrease in the hydroxide concentration, that means that the reaction is going to shift now in the forward direction in order to produce more of it because it wants to reestablish equilibrium. If we think about it as well, we're now decreasing the Q value. So Q value is going to go down, which should then be a smaller value in comparison to K. And so because of that relationship where Q is less than K, it shifts in the forward direction. And so when we think about what answer choice we're going to pick, we're thinking about, well, how is the undissolved magnesium hydroxide going to change? And we're going to say that the amount of it is going to decrease because now it is going to want to shift in that forward direction in order to make more of the hydroxide ions.